Hello, my friends. Yesterday we discussed such a question. The positive integers a, b, and the prime numbers p1, p2, p3, p4, p5 fulfill the following equations. And then we found ab as well as these 5 prime numbers. Today we add the 6th prime number p6 to this question, which indeed increases its difficulty. Then how to solve it now? Let's have a discussion in the following. First, let's briefly review the train of thought we had yesterday. We use the difference of two squares formula to write the 6th power of a minus the 6th power of b as the cube of a plus the cube of b, times the cube of a minus the cube of b. The cube of a plus the cube of b equals p1 times p2, then p3 must equal the cube of a minus the cube of b. The cube of a minus the cube of b can be further factored by using the difference of two cubes formula. Because p3 is a prime number, and the square of a plus the square of b plus a times b is obviously bigger than 1. So a minus b must be equal to 1. One of a and b must be odd and the other is even. Then their product must be an even number. In yesterday's question, a times b has only two prime factors p4 and p5, so one of them is 2 and the other is 3. But in today's question, a times b has 3 prime factors, one of which must be 2, no problem. But the other 2 are not so easy to find. At this time, we need to have some special expectations for the results. If the solutions of the other 2 prime numbers had no pattern, or only very weak pattern, such as 19 and 37, then the question would be a bit too difficult. So we would like to expect that it must include some very small prime numbers, such as 3, 5, or 7. We can start with the smallest one and give a try. That is, we try to figure out what the remainder is when a times b divided by 3. There are 3 possibilities for the remainder of b divided by 3, which are 1, 2 and 0. A minus b equals 1, so the corresponding remainders of dividing a by 3 are 2, 0 and 1. To find the remainder of a times b divided by 3, we can first calculate the product of the remainder of a divided by 3, times the remainder of b divided by 3, then find the remainder of this product divided by 3. This leaves only 2 possibilities, which are 2 and 0. Therefore, if we wanted to prove that a times b is divisible by 3, we in fact need to prove that the case of remainder 2 is not possible. How to prove it? Let's see what other conditions we haven't used. The cube of a plus the cube of b equals p1 times p2, and a plus b equals p1. Applying the sum of two cubes formula, we can find p2, which is equal to the square of a plus the square of b minus a times b. We can then use a equal to b plus 1 in this equation. We calculate it, and find it is actually equal to a times b plus 1. If the remainder of a times b divided by 3 is 2, then p2 must be divisible by 3. And a times b is equal to the product of 3 prime numbers, so its minimum value is equal to 8, plus 1, the minimum value is equal to 9, which is much bigger than 3. So p2 will be a composite number divisible by 3, rather than a prime number. So the remainder of a times b divided by 3 cannot be 2. It can only be 0. In other words, p4 times p5 times p6 must be divisible by 3. One of these 3 prime numbers must be 3. Then we can find the last prime number. If the even number in a and b is equal to 2 multiplied by the last prime number, which differs from 3 by 1, the last prime number must also be 2. If this even number is 2 times 3, which is 6, then the last prime number can be 5, or 7. Are all 3 cases possible? We have to find the other prime numbers and check them one by one. In the first case, a and b are equal to 4 and 3 respectively, p1 is equal to 7, p2 is equal to 13, and p3 is equal to 37. Everything is fine. In the second case, a and b are equal to 6 and 5 respectively, p1 is equal to 11, p2 is equal to 31, p3 is equal to 91. 91 is a composite number, so this case doesn't work. In the third case, a and b are equal to 7 and 6 respectively, p1 is equal to 13, p2 is equal to 43, and p3 is equal to 127, and there is also no problem. So there are 2 sets of solutions to this question. Thank you for watching, and see you next time.